C in a way gives you a lot more expressiveness in the language because of things like unions and structs. There are things you'll be able to do in a dialect of C that would be difficult or impossible to get away with in Fortran.
So if you're going from the Fortran to, say, a CUDA interface, like you were talking about yesterday, then in that case your structs need to be handled or created and handled only in the GPU because you don't have reference to the Fortran interface.
Right.
Or from host side code that
so your C wrapper, your C host side code that one calls the GPU. That's where you could go ahead and take these arrays and assemble the nice structures that the GPU wants.
Okay. So to give you an example, the kernels that I developed for Verichem, the Fortran code just has flat arrays of numbers, and I wanted on the GPU to use float 4s that were packed in a certain way with coordinates in 3 of the values and other quantities in the others, and I had float 2s, float 4s, and another kernel I wrote for another company. They do electromagnetic simulations, and in their case they're doing complex numbers, and so you want to use data in various ways. And so in both of those codes, I basically had the host side code written in C, a little C wrapper, do any manipulations that needed to be done before it got copied to the GPU memory. And then, of course, you can also, your GPU can do these things for itself if there's a convenient means of orienting.
Yeah, but once, that's the question I guess I'm still fuzzy on. I mean, once you forward it to the GPU, you don't want to be rearranging memory, your global memory.
Yeah, you'd prefer not to.
So, I mean, you'd want to do the stuff host side, right?
Yeah, especially if you're going to access it as is. That's true. But there are other kernels where you're going to be loading it from global memory on the GPU, storing it into shared memory, and for the reasons of these bank conflicts and things, you might be swizzling it or spacing them out in various ways to prevent those bank conflicts. If you're doing that stuff anyway, then it's really not a big deal to then consider, well, maybe I want to make a struct out of this for convenient access down in the depths of the kernel's inner loop. So those are different things you can keep in mind.
And how come it was 36 and not multiples of 8?
Jim, maybe you can answer that because I don't know how the name becomes.
So when this code was going in, we were anticipating actually walking, not having every thread simultaneously reading the same value out of shared memory. And if you use a multiple of 8, you have bank conflicts every time, or a multiple of 4, because you're trying to basically walk through. By doing a multiple of a number that is not a power of 2, or basically by doing an odd size, you can have every thread accessing a different bank, or basically when every thread accesses a different element in the array of structs, each thread is accessing a different bank.
This trick of padding things to weird sizes has been around since antiquity. Old Cray machines had heavily banked memory systems, exactly like the way these GPUs are. And so if you go read old Fortran codes, they will often do things like pad things out or size things with a prime number and odd things like this, and that was for exactly the same reason. They were trying to achieve peak bandwidth to the Cray's main memory, heavily banked memory system, same exact concept, preventing multiple vector elements from hitting the same memory bank. So in fact, if you have an old textbook on supercomputing, it'll have all this stuff in it too. So that's been around a long time.
So here, just a few words about the force interpolation that's done. This is what's done with the CPU, where there are table lookups for what we call this A as a function of R squared, B as a function of R squared, and C as a function of R squared. And then the force is calculated as the derivative of this. As the negative derivative of this. And so here, A, B, and C are calculated using a piecewise cubic interpolant, and it's done also so that you can honor the full range of where r squared is changing. It actually digs into the exponent and to determine which window that it should go ahead and do the lookup in. Okay.
And that's kind of an evil trick that you probably have to ask Jim to explain for anything.
Well, I mean, the idea is that, where for small values here, this function is changing very rapidly, so you want, a much finer window size there. And so then you can use the exponent to really determine where you are within, that set of windows. Well, I mean, to avoid that kind of bit manipulation on the GPU, the formulation was rearranged a bit. Now here on the GPU, this reciprocal square root is really easy to calculate, or efficient to calculate. And so instead of a formulation based on r squared, we have a formulation instead where these things are looked up based on the square root of r. And so then, but the interpolation here of these things is this is linear interpolation that's being done for these quantities here. And so we want this to basically be to we formulate this in terms of f over r then, so that basically we can get a linear f of r function at the other end. And so this is the nice trick that Jim implemented in NAMD to make use of this texture unit for silicon. Okay, and so, like I said, the constant memory is used for the exclusion tables. I think I'm going to skip over the details here. Okay, and so the inner loop here that I'm going to show you here on the next page, it only calculates forces for atoms within the cutoff distance, and it's roughly just 10% of the pairs. And so that's one problem that we have here, is that there is quite a bit of work in terms of memory access and in terms of calculating these distance squareds just for then something that we end up throwing away because it doesn't fit within the cutoff distance. So anyway, this gives you a nice presentation of the main part of the NAMD kernel, where the force interpolation, after all of that work to set it up is done, it's a very quick. It's just one line of code here. The exclusions are done using some bit masking tricks here, and so then this is fairly light on computation after this. So this takes care of a lot of the computation that would otherwise have to be done by this kernel. And so here we have the accumulation of the forces, and the NAMD kernel right now doesn't actually calculate energy.
So how about we let them have the break?
Oh, okay, sure.
And then we'll come back after the break, because my next talk I can make short. It's a much simpler talk than this, and this is good material that you guys want to see. So, do we have coffee here yet?
Yes.
Excellent. I think lunch is pizza.